Welcome to Quantum Frontiers, where we venture beyond familiar territory into cutting-edge mysteries of the quantum world. Tonight we'll uncover 5 astonishing puzzles, from fluctuating vacuums and gravity's secrets to exotic particles that could power tomorrow's computers. Get cozy, let go of the day, and prepare to drift into a realm where physics meets dreams. Vacuum fluctuations and the Casimir effect. Even in perfect vacuum, what we think of as empty space, quantum mechanics predicts a restless sea of fleeting particle-antiparticle pairs popping in and out of existence. These vacuum fluctuations create measurable forces. The Casimir effect is the attraction or repulsion between two uncharged metal plates placed a tiny distance apart in vacuum, caused by differences in the allowed vacuum modes between and outside the plates. How it differs from daily observations. In everyday life, empty space feels inert. You don't notice invisible particles materializing around you. Forces between objects arise from classical fields or direct contact, not from nothing. The Casimir effect shows that vacuum is far from empty. Its quantum restlessness can push and pull on physical objects. Why it is important? The Casimir effect provides direct evidence of vacuum energy and confirms a core prediction of quantum field theory that even the lowest energy state has fluctuating fields. It underscores that empty space has structure and energy, with deep implications for particle physics, cosmology, and the search for dark energy. Vacuum fluctuations imply a baseline energy permeating all space. In cosmology, this connects to the cosmological constant driving accelerated expansion. As separations below a micrometer, Casimir forces dominate over gravity and electrostatics, affecting the design and operation of micro electromechanical systems. Precise measurements of the Casimir force test quantum electrodynamics predictions and search for new physics beyond the standard model. Is this possible in the real world? Yes. First measured in 1997 with high precision, the Casimir effect is routinely observed between flat plates, spheres, and other geometries using sensitive atomic force microscopes. Researchers control temperature, plate geometry, and materials to confirm that force magnitude and sign match quantum theory. How it can benefit us? Casimir forces can cause tiny moving parts and MEMS to stick, but engineers are developing coatings and geometries to harness or mitigate these forces for novel sensors and actuators. Concepts propose extracting work from vacuum fluctuations by moving plates or using time-varying boundaries, though practical schemes face fundamental thermodynamic limits. Casimir-based sensors could detect minute changes in separation or force, enabling ultra-precise measurements in material science and biology. Vacuum fluctuations and the Casimir effect reveal that nothingness is alive with quantum activity. By measuring and manipulating these tiny forces, we both confirm deep aspects of quantum field theory and explore new frontiers in nanoengineering and fundamental physics. Quantum gravity. It is the search for a theory that unites quantum mechanics, which governs the very small, and general relativity, which governs the very large, into a single framework. It asks, at the smallest scales of space and time, the Planck scale, does gravity behave like other quantum forces? And is space-time itself quantized into tiny chunks? How it differs from daily life observations. In everyday experience, gravity is smooth and continuous. Apples fall, planets orbit, light bends gently around stars. We never see discrete grains of space or randomly jumping gravitational effects. Quantum mechanics, by contrast, is inherently discrete, with energy, charge, and action coming in quanta. Reconciling these pictures means asking whether spacetime itself has a quantum nature, an idea far removed from anything we observe directly. Why it is important? Without a quantum theory of gravity, our understanding of black holes, the Big Bang, and the unification of forces remains incomplete. At very high energies or extremely small distances, the predictions of quantum mechanics and general relativity conflict, leading to infinities or breakdowns in calculation. A successful quantum gravity theory would resolve these conflicts, offering a coherent description of the universe's birth, the interior of black holes, and the fundamental nature of space and time. Quantum gravity may explain what happens inside a black hole's core and whether singularities truly exist. It could describe the very first moments after the Big Bang, before classical spacetime emerged, shedding light on cosmic inflation and the origin of cosmic structure. A quantum gravity framework might reveal how gravity fits with the other three fundamental forces of footing, magnetism, and the strong and weak nuclear forces, potentially pointing toward a theory of everything. Is this possible in the real world? Researchers are actively developing candidate theories, string theory, loop quantum gravity, and others, but as yet none has been confirmed by experiment. Testing quantum gravity directly is challenging because Planck scale effects occur at energies far beyond current particle accelerators. However, scientists look for indirect signatures, tiny deviations in gravitational waves, imprints in the cosmic microwave background, or modifications to how particles propagate over vast distances. How it can benefit us? Even if practical applications lie far in the future, the mathematical tools born in quantum gravity research, advanced geometry, topology, and quantum information methods often find their way into quantum computing and condensed matter physics. A completed theory could guide new physics beyond the standard model, suggesting novel particles or interactions that might be detectable in next generation experiments. Understanding spacetime's quantum nature reshapes our view of what space, time, and reality itself truly are. Inspired by black hole studies, this idea proposes that all information in a volume of space can be described by data on its boundary surface, hinting that our 3D universe might emerge from two-dimensional quantum bits. John Wheeler coined this term for a wildly fluctuating quantum geometry at the smallest scales, where space-time continuously pops in and out of existence in microscopic bubbles. Projects like the Event Horizon Telescope, gravity wave observatories, and high-energy cosmic ray detectors look for anomalies that quantum gravity might induce. Quantum gravity remains one of physics' greatest open mysteries. By striving to blend the smooth curvature of spacetime with the granular world of quanta, researchers confront the deepest questions of existence, and in doing so, develop new mathematical and experimental tools that could someday revolutionize technology and our understanding of reality. Quantum phase transitions. At everyday temperatures, Materials change state, ice melts, water boils, because heat energy makes atoms jiggle differently. A quantum phase transition happens instead at near absolute zero, where temperature no longer drives change. Instead, you tune a parameter like pressure, magnetic field, or chemical composition, and the material shifts from one quantum ground state to another. How it differs from daily life observations. In our world, you heat or cool things to change their state. You don't normally see a metal turn into an insulator just by adjusting a magnetic field at zero temperature. Quantum phase transitions arise purely from quantum fluctuations, not thermal motion, so they have no everyday analog. Why it is important? These transitions reveal how collective quantum behavior can produce entirely new phases of matter. They expose the competition between different quantum forces inside a material and highlight that even ground states can reorganize dramatically. Studying them deepens our understanding of superconductivity, magnetism, and exotic states like quantum spin liquids. Quantum critical points where the transition occurs often host unusual properties such as very high electrical conductivity or enhanced response to external fields. Different systems share the same critical behavior near transition points, allowing physicists to classify phases by broad university classes. Cold atoms in optical lattices can mimic these transitions under precise control, offering clean platforms to test theories that are hard to solve on paper. Is it possible in the real world? Yes. Experimentalists cool materials like heavy fermion metals or copper oxide superconductors to mill Kelvin temperatures and tune magnetic fields or pressure to find quantum critical points. In parallel, ultra-cold atoms in vacuum chambers form artificial crystals of light, where researchers adjust laser intensity to drive quantum phase changes. How it can benefit us? Understanding high-temperature superconductors may lead to lossless power lines or powerful magnets for medical imaging that work closer to room temperature. Quantum sensors exploit enhanced fluctuations near critical points to detect tiny changes in fields or forces with unprecedented sensitivity. Insights from quantum criticality guide the design of novel materials with tailored electronic, magnetic, or optical properties for future technologies. At the quantum critical point, properties such as electrical resistance follow power laws over many orders of magnitude, unlike classical transitions that only dominate near a specific temperature. Strange metals found near some quantum transitions have resistance rising linearly with temperature, defying standard theories of electron scattering. Theoretical tools like the renormalization group, first developed for thermal transitions, extend to quantum transitions by treating time as an extra dimension, revealing deep connections between space and time at criticality. Quantum phase transitions show that even at zero temperature, materials can undergo radical transformations driven by quantum rules. By uncovering new phases in critical behavior, they open pathways to next generation electronics, sensors, and a richer grasp of collective quantum phenomena. Quantum Hall effect. Imagine a very thin sheet of material cooled to near absolute zero and placed in a strong magnetic field. When you run an electric current along its edge, the voltage across the sheet doesn't change smoothly with the magnetic field or current. Instead, it jumps in exact steps, flat plateaus, at very precise values. These steps occur in units that depend only on fundamental constants, not on the material's details. That is the quantum Hall effect. How it differs from daily life observations. In everyday circuits, resistance and voltage vary gradually with temperature, material impurities, or applied fields. You wouldn't expect perfectly flat exact jumps in resistance. The quantum Hall effect shows that at extreme conditions, low temperature and high magnetic fields, electrons organize into collective quantum states that produce exact, unchanging voltage ratios. Why it is important? Discovered in 1980 by Klaus von Klitzing, it revealed that electrons in two dimensions can form new topological phases of matter. These phases are characterized by global properties, topological invariants, that remain fixed unless the system undergoes a dramatic change. This shifted how physicists understand phases, moving beyond simple categories like solid or liquid to a richer classification based on quantum geometry. The quantum Hall effect provides an exact reference for electrical resistance, used worldwide to define and calibrate the ohm with unrivaled precision. It opened the field of topological insulators and superconductors, materials that conduct electricity on their edges or surfaces while remaining insulating inside. The effect connects to advanced concepts like Chern numbers and periphases, linking condensed matter physics to quantum field theory and geometry. Is this possible in the real world? Yes. Metrology labs around the world exploit the quantum Hall effect to maintain national standards of resistance. By cooling semiconductor devices or graphene sheets and applying magnetic fields, they achieve plateaus accurate to 1 part in a billion. How it can benefit us? Guarantees that gadgets ranging from multimeters to industrial sensors remain accurate over decades. Insights from topological states inspire new electronic components that are resistant to defects and disorder, promising more robust devices. Topological qubits designed to store information in global properties, immune to local errors, build on the same principles that give rise to the quantum Hall effect. There are both integer and fractional quantum Hall effects. The fractional version, discovered in 1982, shows that electrons can combine into quasiparticles with fractions of an electron's charge. Graphene, a single layer of carbon atoms, exhibits the effect even at room temperature under strong fields, opening possibilities for practical devices outside specialized labs. The effect inspired Nobel Prizes in 1985 for von Klitzing and in 1998 for the discovery of the fractional effect, highlighting its foundational role in modern physics. The quantum Hall effect reveals how collective quantum behavior in two dimensions can produce exact, unchanging electrical properties, linking the bizarre world of topology to the precision tools that power our technology.